Hello, students. I hope you can hear me. I wanted to do a recording for this related to the work in this upcoming assignment because the previous lab, we talked some about this, but not very systematically. So yeah, I'm not going to be working with a language that is the same as Patina or anything really like it, but the same sort of rules should still apply, same procedures. So here we have this random language that I came up with. So we have each program is a list of blocks. Each of these blocks is a list of statements or expressions. And inside the expressions, we have plus, minus, times, divided by, and we also have L and A for lambda and for application. They're used for functions. What matters here is that both of them, well, L takes the arguments first, and then what is returned from the argument. So here, when we're taking sum of 3, then we look at this sum of 3, which will end up having the value 3. But we can see if we take that value and we change x around, and if we make x a different number, then this is the function just x plus 1. So that's why it's called add 1. So this right here is always going to be an identifier, such as x here. It could also be sum 3, basically anything like that. Application, on the other hand, the first thing is always going to be, in this case, both of them can be whatever sort of expression. The expressions don't need to have names. So here we have the 2 has a name, which is x. But like the x minus 1 doesn't have a name. Yeah. These intermediate steps don't have names. So yeah, so we have this structure here, and we're going to try to parse it into this AST that I have. So here you can see that we have integer constants. The if is just going to work by checking if it's equal to 0 or not. And oh yes, our bin-ups need to have less than and less than or equal to. Anyways, we can have constant integers. We can have variables that have been named before. We can just fail. We can have a binary operator that works on 2 expressions, such as our plus or our less than. We can have a block which restricts the scope of the variables defined within. We can have a lambda expression. So you can see, actually, for convenience's sake, let's put the string first to match what we have. We have an application of some function to some value. We have ifs, which take in an expression and then return one of 2 expressions. And we can also have a return statement. And so the return statement is what the block is going to return. So here, block 1 is going to end up having the value of add. This is some garbage language. Like the point isn't that this is good. The point is, okay, here we have a language, we have an AST that we're trying to parse it into. how do we go about writing the parser for it? So one of the first things that we need to do is we need to come up with all the different tokens that we're going to be that the parser is going to have to work with. So here we have basically a bunch of things that look like this, hashtag token. So I'm going to start typing them in. So we have a token, which is a, what do we have here? We have equal sign. So let's do an equals. We have a left open L brace and R brace. We have return. We have plus and minus. So plus, minus, times, divide, less than, less equal. You can always swap the order of the things to these to get greater than or equal to. What other tokens do we need to have? We have a semicolon at the end. And parentheses. So L paren and R paren. It looks like that's everything here. Maybe return is its own. Yeah, we got that one. L and A. So since those are specifically reserved to mean lambda and application, we need to make them token. We should make them tokens themselves. And now I think that's it. That should be all of the tokens that we have. So then, well, we can work on the lexer, but let's work on the parser first. So, oh, integers. We're missing integers, and we're also missing strings. So this is the syntax here is we say what type it is here. So here we have a string, which is, and we can also have an int ident for identifier. So now if we encounter an int, we can just take the value directly and pass it in. Well, we could make this a string and then we can convert it in the parser. I guess that could also work. Let's do that. All right. So main, we're going to be trying to return a prog type here, which means we need to define prog in a way that will have that it'll be a list of blocks. Okay, so actually, I think it's and actually, based on this example, this AST isn't quite right. It's actually just an expression list. It's just a block. But unlike these blocks, we don't have curly braces around the whole thing. So, all right, we just have an expression list. So an expression list, we're going to assume that it's non-empty because otherwise the file is empty. and it's not, this doesn't make much sense to try to parse it. So we say that prog is going to be equal to either a expression, or it's going to be equal to and then a semicolon, or it's going to be equal to some an expression, a semicolon, and then a prog, right? Because here, if we get rid of this first one, this is still a program. We just have the blocks one at a time. So we're sort of doing this recursively. The prog can have a prog inside it. All right, but now we haven't defined what expr is. So then we need to define that. So expr here, and based on the AST, we can see it'll probably be pretty complicated. So we could actually separate this out into the easier ones and the harder ones, maybe. So we can say that an expr is either a easy expr or a hard expr. You can just come up with these however you like. I noticed we didn't say what these values are. So here, remember, it's supposed to be a list of expressions. So whatever this expr here returns, it should be an AST expression. So here we just do $1. And here, again, we're trying to make sure it's a list. So here, since this is a list, then we can just concatenate this onto the front of it, or not concatenate. Or maybe that's the right word. Anyway, you can use $1 concatenated to prog, or $3 in this case. And in this case, it's just the thing, so no point doing anything else there. So for the easy expressions, let's say we have, we want to work on, say, fail. I guess we can add in a token for fail. So if we see the token fail, then we know to return perhaps actually here we can name this something else. Let me check if here I named it something else. No, I didn't. That's a little annoying. Well, we can just copy paste whatever. So here we can say it's .fail because it's the fail coming from this file. If we get, what other things can we get that are relatively easy? Const, a var. These are all the ones that don't involve any sort of recursion. Oh, you might notice, oh, actually, I'm doing an expr list here, but it's supposed to be an expression list, right? An expression is this record. So let's fix that. So what needs to be fixed here? This doesn't need to be fixed because it's still a list. This one doesn't even necessarily need to be fixed. But let's fix them here. So maybe we can say this should be expression semicolon, so that it properly reflects what we want, which is an expr, which can have this x equals, you can name it at the beginning, or you can just not name it. So we'll give those two possibilities. So possibility one, and let's get rid of this for now. Possibility one is we name it. So here we would have an ident, and then we would have an equals, and then we would have an expr. The other option is just having an expr. And in this case, you'll notice that ID is a string option. So now we need to make them here. So here it's none because we're not given a name. So we would say that ID is none. And we would also say that value is equal to $1, whatever expr returns here. But this isn't actually right because these curly braces here, you need curly braces to correspond to the record type to create a record. But we're also using it just for the .mly format. So we need to put in an extra pair of curly braces here. And then for this one, we have, again, it still needs to be a string option. So ident here is a string. So we can say sum of $1. And then value, basically the same sort of thing. The value is $3. And yes, we have these double curly braces around it. Okay, now we can get to expr. So here we have our expressions can be a whole lot of things. Let's go through them one at a time, I guess. Const of int. So in what cases are we going to want to say that our expr is a const? Basically just the cases where just an int is returned. So if we have just an int is returned, then we're going to want to, remember it's a string, so we're going to want to make a const of an int. So this should say const of something here. But we can't say $1 because this is a string actually. So we need to use Ocaml's just int of string, which I'm pretty sure is how you is the standard library way of doing that. So we take this int, string, we turn it into an int, and then we create this expr out of it. So that was nice and easy. So what do we do for var? So ident, and we're going to want to create var of some string. Here it's actually, again, pretty easy. We just do $1. Yeah. Okay, next one, fail. In which cases do we want to return a fail? We want to return a fail in the cases where there's just fails written. So this is the easiest one yet. We just do fail. I think some of these we might need to copy and paste this everywhere, which is a pain, but well, yeah. Anywhere where there's one of these constructors. But I'm not going to bother with that because it's the sort of thing that might be different based on the Dune environment and everything. This is the parsing. Okay, so bin op. Let's do this. So which cases are you going to have a bin op? When you have a bin op in the middle and expressions to the left and right. So here we can, a lot of the parsing can just be almost copied directly from the AST definition. Like we still need to make some changes, like we need to do this int of string, we need to create these records here, but a lot of it can be, it's basically you just take the concepts that are in the AST and convert them into the correct format. So in a binop, we're going to have a binop in the middle of two expressions. This expression thing is kind of long. Let's make it a little bit shorter. All right, this seems decent. Expers, it might imply plural, but well. We have an expression and then a binop and then another expression. And so if we want to create a binop expert type here, then we just need to do binop of $1, $2, $3, checking to make sure that, yes, it's the correct order here. And that expression is the type that we want. So here we're using expers. So we're expecting something that could have an equals at the front of it. Right. So then block, we can have a block. This is basically just, we can have a L brace. And then we can have, well, let's look at the sample. What's inside here is actually pretty similar to what's outside here. So it's basically a prog. So we don't need to come up with a new block system. We can just do this. So here, then, well, what does a prog return? Prog returns a list of expressions. And a list of expressions is a block, which means it's the right type to pass into expert here, the block constructor. So block of 2. So you just continue along there. It's pretty much the same sort of thing. Binops are going to need to be defined above. So binop here, we just have, okay, what if we have a this here? Sorry, a less than. Well, that gets converted into, surprise, surprise, less than. And this is the right type. This is a binop type, which is what we want to end up passing into as an argument to this binop constructor here. So again, this just goes on. And after that, that'll actually be all of the important types that we have, because I picked a pretty simple structure. And also there might be more complicated things later on. Let me think about it for a bit. If we have a lambda, if we have an application, it's essentially just the same thing. We have, as the binop, we have an A or an L telling us, okay, we're going to be doing things with these two expressions. And yeah, then we have it. Maybe let's look at if. We could even have this thing have an optional else. So here we would say that it's an expression option, where if there's no else and it doesn't happen, then it just returns a fail, or something like that. Some fixed value. Again, I'm not going to be running this code, so it doesn't really matter. But it is useful to look at, okay, what do we do when we have these options? So if we have we can just write down two options. For one of them is, okay, if we have an if and then an expression and then a then, I realize I forgot to put if and then and else. We can do this here. And then this would have a $1, $2, $4, and none. And then the same thing if we have an else in here, where we just simply put in sum of $6. Hopefully this makes sense. All right, let's look at the Lexer now. So this is your starter code. This is the basic, we want to say for a regular expression that a regular expression has, for a variable name, has to start with some alphanumeric thing, and then it has to continue with, or it has to start with an alphabet character, and then it has to continue with alphabets or numbers or underscores to any degree. So yeah, so in this case, we would want to say, okay, this gets parsed in as a, okay, so this is the general string case, right? General variable name first, but we have to deal with all of the other constants first. So in our sample, we have return, for example, which needs to, well, it needs to return a something of one of these tokens here. So here we can just say return, and this is going to and this here is going to well, it's going to do this, but first we want to turn it into, we want to turn it into a token. So we just want to turn it into return, similar to EOF. And then we just do this for all of them. So you can see here, I took lparen, rparen. This is kind of, I mean, you just have to do it for each of them. The interesting part comes in with the, with this here. So what do we do with this? And there's a couple of ways of doing it. So one way of doing it, what we're going to end up with is a string, and we're going to want to make that string an ident, right? Actually, we're probably going to want to have an int first, so the int is not going to have any alphanumeric stuff. It'll just be numbers, something like this. And then in here is going to go something like int of the particular thing it is. So here you can see you say as of whatever. You just give it a name. So int this thing as LXM, and then I take, okay, this is going to be int of LXM. Same sort of thing here, as whatever ID LXM, it doesn't matter. And then I just say, okay, this is going to be, and you have to make sure that you're using the same names for things in the parser and in the lexer, because they're trying to work together. So I take, okay, this is an ident of LXM, of ID LXM. And then you just fill this out with all the different um, constant ones. Okay, so I hope that was clarifying, and good luck with your assignment too.